Okay, so yeah, we will finish the spectral clustering today, and yeah, last time we went through this interesting relationship. So this matrix L, which we call a Laplacian matrix, where we have the diagonal entries in the middle, and then for the off-diagonal entries, they have a adjacency weight or the edge weight, but it's a negative value of edge weights, right? And then basically this L is the same as d minus w, okay? D minus w, and then on the right, on the left and the right, we will consider multiplying the same vector as a row vector on the left and the column vector on the right, and then altogether it will produce the square. It will produce the scalar value, and that scalar value, after some derivation, it will become. Let's see. It will become this form. Okay. So for this vector f, we have freedom to choose whatever values contained in the vector f, but this scalar value will have this weighted sum, where the weight is our edge weights from the adjacency matrix W, and at the same time, this term is a squared difference between the two elements or two scalar values in f vector. Okay, so in general, our problem here is to minimize this guy. Okay, we want to minimize that, and intuitively, if this weight is large, and then we have to make this difference between these two elements to be small. Okay, so as a intuitive example, so if we have these three nodes, and then the edge weight is like 100 and 10 and 1, and then we are considering the three-dimensional vector of an f, and then if this value was maybe 5, and since the edge weight between the node 1 and 2 is really large, we have to make this value to be really close to the scalar value of this 5, okay? Because this one is f1 and f2, and from the previous equation, we are considering this weighted squared sum of f1 minus f2 squared, and this one is w12, right? So those two values to be really close to each other, but if these two, I mean the edges between these two, are really low value, and then we are free to have a relatively large differences between f1 and f3. Okay, and also if this one becomes 0, which means there is no edges between these two nodes, and then we don't incur or we don't cause any loss values, even if this value and maybe this value is maybe 40, and then in this case it will have 35 squared, but the corresponding edge will become 0. Okay, so that's the intuition to optimally choose this vector f. Okay, but now we will consider using this kind of intuition, we will introduce or incorporate some mathematical notion of this eigenvalue and eigenvector in this case. Okay, so this problem of this minimization problem. So this L should be some square matrix. So suppose L was 5 by 5 matrix. So even though this guy is a Laplacian matrix, but it can be any matrix. So it can be your covariance matrix, or it can be any other kind of square matrix. Okay, and then you can consider this kind of problem. It will generate always a scalar value, and then which vector f will minimize this scalar value. Okay, and then if we do not impose any constraint, if we have no constraint, and then this problem may become really trivial, because if f becomes a zero vector, so we have all zero elements in f, and then we can trivially make them as zero. Okay, and so here we have this kind of constraint, so that the 2 norm of an f, the vector f, remains the same as just 1. Okay, so we consider only the unit vector which has the length of 1. Okay, so that way we can avoid this kind of the case of trivially making them as 0 and so on. And so by having this kind of constraint, now our focus is to find the optimal angle of this vector f. Okay, so you guys understand why we care mainly about the angle in this problem. Okay, and what should be the optimal angle for this vector f, and what determines that optimal angle with respect to this matrix L. Okay, so in general, this problem is called Rayleigh quotient. Yeah, Rayleigh quotient, and theoretically, this value is minimized when f is eigenvector with the smallest eigenvalue. Okay, so this is a kind of theoretically known, and let's see why. Okay, so what was the property of an eigen decomposition? So we have a matrix L, which is a square matrix, and then we have a vector f. Let's consider it as a eigen vector, and we have some lambda, and we have some f, right? And in this case, if this f is one of your eigenvector, and then it will become this scalar times a vector f. Okay, in this case, we have f transpose and L and f, right? And then this part will become some eigenvalue lambda and f, right? And so we are multiplying them together, and then we have lambda here and f transpose and f here, right? And in this case, this part is will be the same as f2 norm squared, which is 1. Okay, so that way, if this lambda becomes the smallest, and then this is your solution, or the optimal minimal value. Okay, so that way we can kind of get some intuitive understanding about why it should be smallest eigenvalue. Because if you have maybe three eigenvectors, maybe 1, 2, 1, 0, 2, -1, and 3, 2, 1. So suppose you have 3 eigenvector, and then the corresponding eigenvalues are maybe 5, 2, 1, and then this vector will be the one to choose, right? Because it will have a smallest eigenvalue. Okay, and then what about the combinations of them? So we are not restricted to just to choose only among the eigenvector. We have a freedom to choose any vector, not just limited to eigenvector, right? But in this case, so if you study the eigen decomposition, and then you are understanding that any vector f can be represented as a linear combination of some basis vector. So if it was a three-dimensional, so L was 3 by 3 matrix. So in this case, suppose you have these three linearly independent eigenvector, okay, and then you can represent any of your vector using the linear combination of the new basis vector, which are your eigenvectors, right? So in this case, suppose your f was 2 times this plus maybe 1 times this plus 5 times this. So these are your linear combination coefficient, okay? And in this case, what would be L times f? So this L times f became some scalar times a vector, right? The same vector, eigenvector, which is your eigenvector. And in this case, if your vector f was a linear combination of those, and then when multiplying the matrix L on the left, and then this part will become the same vector 1, 2, 1 and 2 times 5, so 10, right? So your original linear combination coefficient multiplied by the corresponding eigen values, right? So that's the result of L times f, okay? And then yes, suppose so let's further assume that these eigenvectors are orthogonal to each other, so they are perpendicular to each other. So in this case, so it's like, let's see, so it's 10, let me use a 10 times, so it will be 2 and it will be 5, okay? And then you are multiplying this guy, on the left we are considering like a 2, 1 and 5 with the same, so basically we are multiplying f transpose, and then it will be 2 times the transpose vector f1 plus 1 times the transpose vector of this guy and plus 5 times this, right? And so this one will be placed on the left. And then if they are multiplied together, so on the left you have 3 vectors, and then on the right you have 3 vectors, right? And then the summation of the two set of 3 vectors, they are multiplied together, and then we will have, so it's like something like this. 215 2xy plus 5z times so it's like a transpose, right? And then 10 times x plus 2y plus 5z, right? And then we have this self term, right, multiplied by itself, and also we have some cross terms multiplied between different vectors, between x transpose and y, x transpose z, and so on. So if they are perpendicular to each other, and then the cross term will become all 0 because they are orthogonal to each other, so their inner product will become 0. And so it will be something like, so the remaining or the surviving terms will be all self-multiplied terms, like x transpose x and 2 times 10, right? 20 plus 2 times y transpose y plus 25 z transpose and z, right? So each of them will be 1 because they are just inner product with itself, which is the same as the norm of x, norm of y, norm of z, and then the resulting value will be 20 plus 2 plus 25, right? So far so good, right? And then now let's look again at our constraint of this guy. So in this case, so suppose our eigenvectors are all having a unit length, or the length of 1, and then now our new vector f, that can be a linear combination of our eigenvectors, right? So yeah, so we have these 3 vectors, right? And then we have a freedom to choose the linear combination coefficient between these 3, right? Among these 3. But we have to obey, or we have to follow the constraint that the resulting vector f, that should also have the length of 1. So it's like, so we cannot like freely enlarge or increase the length of our resulting vector from this linear combination. Okay, so it's like we are kind of distributing what we have, or the total amount of linear combination coefficient to 3 of them. Okay, so if we assign here maybe 0.7, and then we are only assigning up to 0.2 and 0.1. So that way we can kind of obey the length of the vector f to be 1. Okay, so although it's based on L1 norm, but in the case of an L2 norm, you can think of it in a similar manner. So we are distributing carefully those linear combination coefficients to each of our eigenvectors, which are our bases. Okay, and then you guys know that for each eigenvectors, we are multiplying their corresponding eigenvalues, right? So in order to minimize the total sum after doing this kind of computation, our best strategy is to assign all the weights, all the linear combination coefficient to the eigenvector with that have the minimum or the smallest eigenvalue. Yeah. So our best strategy will become 0, 0, 0, and 1. Because if we had a maybe 0.1 and 0.9 and 0.8, and then this one will be amplified by the factor of 5, which is the largest eigenvalue, and then this guy will also be amplified by the second largest eigenvalue, and so on. And so in order to minimize this amplification, okay, we have to assign all the linear combination coefficient to this smallest eigenvalue, smallest eigenvector. So that's why the optimal solution for this vector f, even though we have a freedom to choose, or even though we have a freedom to linearly combine these eigenvectors, but the optimal solution will be to just pick up or assign the entire linear combination coefficient onto this smallest eigenvector. Okay, so that is kind of intuition for why this optimal solution for this Rayleigh quotient is this eigenvector corresponding to the smallest eigenvalue. Okay, so this problem is quite used in many different areas. So you might see this kind of Rayleigh quotient or this kind of optimization formulation in some other applications or in your research areas as well. Okay, and then then how can we guarantee then? So I made a few assumptions that these eigenvectors should be orthogonal to each other, which means we have a kind of eigenvectors that are orthogonal to each other or perpendicular to each other. And so this kind of assumption is true in the case when this matrix L is what? L is symmetric. So if your matrix L is symmetric matrix, and then symmetric matrix will always have a eigen decomposition, which means, so if it was 3 by 3 matrix, and then you will be guaranteed to have 3 linearly independent eigenvectors, which means this matrix L has the eigenvectors that can span entirely your 3-dimensional space. Okay, so that's one of the nice property of this symmetric matrix. And then also symmetric positive definite or semi-positive positive semi-definite, PD or PSD. And that means what? Yeah, in this case, the eigenvalues are non-negative. So you don't have any negative eigenvalues. And this symmetric and positive semi-definite is a kind of typical or common assumption that is used when formulating some problem as this Rayleigh quotient problem. Okay, so yeah, it is almost always the case that L is always like a symmetric and positive semi-definite when L is used in this Rayleigh quotient problem. Okay, and so in this case, let me ask one question. So if your matrix is not positive definite or positive semi-definite, and then your matrix can have a negative eigenvalue, right? So instead of 5, 2, 1, suppose you had 5, 2, minus 1, for example. In this case, this Rayleigh quotient or this scalar value can become what? It can become negative value. Okay, because so suppose you gave all the linear combination coefficient to the smallest eigenvalue. In this case, still this value or this value will become 1, which is always a positive value, and then the resulting value lambda will be what? The same as the eigenvalue, which is minus 1 in this case, right? And then will it be possible? Will it be possible specifically in our example? So even without using any kind of knowledge about eigenvalue or eigenvectors, we successfully derived this kind of formula, or this guy is the same as this, right? And then from looking at the form of this guy, we can guarantee that this guy is always, always a non-negative, right? As long as our edge weights are all non-negative. Okay, so even though I will not prove this, but if your adjacency matrix is non-negative, which means you don't assume any negative edge. Okay, you don't assume any negative edges, and then your matrix L or this Laplacian matrix L is guaranteed to be this positive definite or positive semi-definite. Okay, it's quite a linear algebraic thing, but yeah. Okay, so let me get back to this problem of this Rayleigh quotient or minimizing this guy. Okay, and then so this one has the minimum of 0, and then as we discussed last time, we can trivially make this guy as 0 by setting f as all ones. So in this case, this part will become always 0. So regardless of any weight, and then we can have a perfect the minimum value of 0. So in this case, from the eigenvector and eigenvalue thing, this guy or this kind of understanding in terms of an eigenvector vectors. So the optimal solution for this Rayleigh quotient problem is the eigenvector with the smallest eigenvalue, right? And then this 1 and 1, this guy achieved the smallest value in this objective criteria, which means this guy will become your eigenvector that is that has the smallest eigenvalue. Okay, so how can we verify this guy is eigenvector? So when constructing L, so suppose we have 1, 2, 3, 4, 5, 4, and 1, 2, 3, 5, 4. So you can easily imagine what the result corresponding graph is. So this is just an adjacency matrix, right? So we have 4 nodes, and then the edges between them will have 1, 2, 3, 5, 4, and 6, and so on, right? And then what will be our Laplacian matrix? Laplacian matrix will become, we'll put the minus sign here, right? And then what is the diagonal entries? What is the first diagonal entry? What is the value here? So by the definition, L is D minus A, and you guys know what A is, adjacency matrix is. Then what was this D? What was D?
Minus 6.
It is 6. So you are simply, so it's like, so we have node 1 and node 2, 3, 4. And then the edges, 2, 3, 4. Edges are, edge weights are 1, 2, 3, right? And then what was the degree? The definition of the degree, or in general, the degree matrix. In the diagonal, we are summing up all the edges, edge weights, and then that will become your degree of the first node. And what about the second node? This guy? It should be 10. And what about this guy? Then 13. Okay, and then let's think about the eigen decomposition using this matrix L. Okay, so I mentioned that we have a eigen vector of all ones, right? And then what will be the corresponding eigenvalue? Lambda. Or what will be the resulting vector after doing this matrix vector multiplication? So what is the first entry?
0.
So it's like we are summing up the first row, right? And then first row should be, the summation of the first row should be 0, and the second and the third and so on, right? So for all rows, as we sum them up, each row, as we sum each row up, and then the resulting value will always be 0. And why? It is because we set our diagonal values to be that way, right? This the diagonal value will be the summation of each row, yeah, except for the negative sign, right? So that's how we set, how we compute, or that's how we obtain the degree value of each node, right? So for this Laplacian matrix, from the definition of D minus L, okay? So if we use this guy, okay, all ones as an eigenvalue, and then we will always end up with the zero zero vector, which is 0 times 1. So that way this guy will satisfy this equation, and then the corresponding eigenvalue will become 0, right? And so yeah, by looking at this direction from this perspective, it also verifies our kind of intuitive understanding, or our knowledge that this guy should be the optimal solution, and also the resulting value of this guy will become the value, where the eigenvalue will become 0. Okay, and then that solution can be also understood by setting all these values to be all equal to each other, right? Okay, then this was the one block case, or this is a kind of always true in any of your graph. But if you have like sub blocks, so suppose we have this kind of sub graphs in our entire graph. So we have a 5 node, and then we have a connection between the first group and the second group, but not between different groups. Yeah, we have no edges, right? So in this case, we can think about this block diagonal structure in our adjacency matrix A. So we have no edges. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we shouldn't see any edges between this group and this group. So that way we see all 0 values here. Okay. So in this case, in this case, unlike the previous example, the possible solution of making this value as 0. Okay, so we want to make them as 0. Okay, so we now have a more choices, or like additional solutions other than all ones. Okay, so this all ones will still make this guy to be exactly 0, right? Because we have this, right? It's getting dirtier. Yeah, so we have this. So okay, and then the other possible solutions, the other possible f that will make this guy still as 0 can be this 1, 1, 2, 2, 2, 2, 2, or maybe 3, 3, minus 1, minus 1, minus 1. Okay, so in this case, from this guy, wij fi minus fj squared. Okay, so in this case, as long as we have a same values when they have an edges, or within the same groups, okay, and then their value should be the same, but we don't need to have the same values between the nodes, between different groups, right? So because in the case of 1 and 3, and we are comparing these two, 3 minus minus 1 squared, which is non-zero, but fortunately this edge will become 0. Okay, so okay, and then this guy is always achieving 0, which means this guy also can become your eigenvector, which means you have a L here, this L, and let's imagine L times this vector, and then it will always give you 0 values, 0 vectors, right? Which means this guy can be always represented as 0 times this vector, 1, 1, 2, 2, 2. So all of these are your eigenvectors. Okay, but so you can see that there can be so many different eigenvectors, but among all these eigenvectors, you have to follow these kind of constraints within the same group where the edges are non-zero, and then they should have the same value, but between different groups where there is no edges between them, and then you can you can freely change these. You can freely have a different values between different groups. Okay, so in this case, let's consider the linearly independent basis that can represent all these possible eigenvectors. Sorry. In this case, let me give a one set of bases. So the basis will be 2, and then it will be this and 0, 0, 1, 1, 1. Okay, so this is a simplest set of your bases, and then using these two, you can represent any vectors like this and so on, right? So these two are, among the many, these two are one set of linearly independent eigenvectors. So the bases have 2 vectors. So the dimension of this subspace is 2. And so you can think of it as like you now have one more dimensions or one more degree of freedom in manipulating or creating your eigenvalues, or in optimal solutions for this f. You can freely combine or linearly combine these 2 vectors. And what about the 3 groups and 4 groups? In that case, you can think about like in the case of 4 groups, and then you can think of like a 1, 1, 0, 0, 0, and then 0, 0, 1, 1, 1, and 0, 0, 0, and so on. And so that way, you can have like a 4 linearly independent basis vectors that can span, that allows you to represent any possible eigenvectors. Okay. So in this case, if you perform eigendecomposition, so what is the step of computing eigendecomposition? First is what? Do we compute eigenvalue or eigenvector? I mean, at first, which one is the first step? Eigenvalue or eigenvector? Eigenvalue. And how do we compute the eigenvalue? So we construct some equation, and what is that equation? Determinant A minus lambda I, right? So this one, in the case of A being a 3 by 3 matrix, then it will become a third order polynomial in terms of a lambda. And this third order polynomial, just like lambda squared, maybe 2 lambda cubic and squared, and then minus lambda plus 5 equals 0. So you will have this kind of equation or polynomial equation, and then you will always have the solution of 0, because you know 0 will be your eigenvalue in this case. And then when setting lambda as 0, and then you will see the second step will be to compute this vector x, or obtain the non-zero vector x that satisfies this equation. And so lambda is a 0, and so it's like a times x is 0, right? And then in this case, if they have just one single group, and then this vector x will become just only one vector of 1, 1, 1, 1. And also, if you have like 2 groups where this A, or your matrix L, which is a Laplacian matrix, if that matrix has this kind of sub-block structure, and then this X will give you 2 different eigenvectors. And the number of this eigenvectors for the single eigenvalue, what was the name of it? So the number of linearly independent eigenvalue, the number of number of linearly independent eigenvectors corresponding to one single eigenvalue. What was the name of it? Yeah, it's called a multiplicity. And which multiplicity? Which multiplicity? Which multiplicity? Geometric multiplicity. Okay. And what was the antonym for it? Algebraic multiplicity. Okay, so that's although it's like a undergrad level linear algebra, but yeah, let's not go deeper at this point. But anyways, so if you perform this eigen decomposition, and then the number of linearly independent eigenvectors corresponding to the smallest eigenvalue 0 will be actually will be the same as your number of subplots in your matrix L. So what was our main goal of all these different formula and this kind of mathematically tricky things? So we want to do clustering, right? So we want to perform clustering. So we want to find some group and their grouping membership, right? And so in this case, if you perform the eigen decomposition on this L, okay, then let's just sort the eigenvalues, okay, eigenvalues. And in this case, if you found two linearly independent eigenvectors, and then let's count it like redundantly. So this guy is eigenvalue having an eigenvalue of 0, and this guy is also 0, and so on. So you just sort these eigenvalues, and this is an eigenvalue, okay? And this guy is just a sorted order. 1, 2, 3, and 4, and so on. And your eigenvalue will be revealed after performing the eigen decomposition on L. You will see the eigenvalue of something like this. Okay, so you have maybe a 100 by 100 matrix where your number of nodes is 100. So in this case, eigenvalues, after sorting them out and then just drawing them in this manner, just sort them out and then map the y value as your eigenvalue. And then suppose you are observing this kind of pattern. In this case, how many groups can you conclude to exist? So how many groups do you think of in your graph L, which is composed of 100 by 100 nodes? So the fact that we see 3 zeros as your eigenvalues, and then it means it has some linearly independent eigenvectors with the same value of same eigenvalue of 0. So in this case, we can conclude that there exists 3 groups, right? Oops. Oh, where is it? Okay, so if you see many number of 0 eigenvalues, and then it means your graph will have many number of groups, okay, subgroups. And what is the pattern for these eigenvectors? So we don't know what particular set of eigenvectors will we obtain? Okay, we don't know what particular eigenvectors we obtain, but we always know that these vectors will have the same value within the same group, but possibly different values between different groups. Just like this kind of pattern: 1, 1, and 2, 2, 2, and 3, 3, and minus 1, and 1, and 1. And in these two cases, one common fact is that within the same group, they will have always the same value, even though that value can be 1, or minus 1, or 3, and so on, right? But within the same group, the corresponding node, the values, elements will have the same value, right? So if we have a 3 groups, and then what we don't know is their grouping membership or cluster membership, right? But in these 3 cases, suppose we kind of observe that, okay, 1, 4, 7, 10, those 4 nodes, the first and fourth and seventh and 10th node value had almost the same values, okay, in all these 3 vectors, right? In that case, we can kind of conclude that, oh, those 4 nodes are belonging to the same group, okay, from this kind of pattern. So that is a main intuition of this spectral clustering. So so in back to this simpler case where we have 2 groups, and then what if we observe, unfortunately, this kind of thing: 1, 1, 1, 1, 1. So this one is also satisfying, satisfying our requirement that within each group they have the same values, right? But in this case, they do not tell you these 2 groups are different groups, right? So when looking at one eigenvector, one of the eigenvectors, and then it can be something like this. So suppose you have 100 different nodes, and then you have 3 groups, and then 3 groups is composed. 3 groups are composed of 30 node and 30 node and 40 nodes, and you just draw one of your eigenvector. So eigenvector dimension will be 100, and y value is the value of each element in your eigenvector. And in this case, it can be possibly like this, so all the same values, okay? Or it can be like the same values up to 30 points, and different values up to 70 points, and up to 100 points you may see like a different pattern. So if you draw one eigenvector, and then the graph will be something like this, okay? So this one is just nothing but this 3, 3, minus 1, minus 1, minus 1, and 1, 1, 2, 2, 2, and so on, right? So one eigenvector could be this, and then the other eigenvector could be something like this, and so on, right? But unfortunately, in some eigenvectors, they may not clearly distinguish between different groups. For example, let's see, okay, like this. So in this case, unfortunately, it didn't distinguish between the first and the second group, because we do not have any constraint that the value, the value shouldn't, value don't need to be different between different groups, right? The only assumption or only requirement is that within the same group, the value should remain the same, okay? We are not restricting anything between different groups, right? So that way, we may observe the same values between different groups. So by observing one eigenvector, okay, that eigenvector may not reveal fully all the different groups. So in this particular eigenvector, unfortunately, it can reveal only two groups, okay, and one group may contain multiple different groups, okay, but but in this case, suppose you have a three zero eigenvalues just like this, and then you collected all these three linearly independent eigenvectors, and then you just integrate them in order to obtain the conclusion, in order to obtain the cluster membership. Okay, so one is not revealing the first and the third group, first and the second group, just like this. But in the second or the third eigenvalues, they should distinguish. They should distinguish between the first and the second group. So in the first eigenvalue, they didn't distinguish between the first and the second groups, but they will eventually be distinguished between. I mean, they will be distinguished in the second eigenvalue or later in the second eigenvectors or later eigenvectors. Okay, so if we combine all the information from all these eigenvectors that is belonging to all zero eigenvalues, and then altogether they will tell you different groupings. Okay, so this is a main idea of spectral clustering. So we are now ready to talk about the detailed steps of an spectral decomposition. Spectral clustering. So the spectral clustering is working as follows. So you construct this L, and you just perform the eigen decomposition. Okay, and then you find out those eigenvectors that are linearly after performing eigen decomposition, and then you pick up eigenvectors that are belonging to zero eigenvalues, and then you formed 100 vectors from the first eigenvector, and then second and the third, and you have 100 by 3 matrix, where the first column is the first eigenvector, and the second eigenvector, and the third eigenvector. Okay, and then now we view it row by row. So in this case, you view the new reduced dimensional representation of the first data item from the first row, okay, and the second row and the third row, and now you suddenly have three-dimensional vector representation of 100 data items from just the compiling or from just concatenating your three eigenvectors. Okay, and then these three-dimensional vectors are revealing your cluster structures. So from this three-dimensional vector representation, you perform some basic clustering methods like k-means. But this clustering method can be like a different clustering methods, like a hierarchical clustering and so on. But here the main intuition is, after you obtain this dimension reduction representation using eigenvectors with zero eigenvalues, and in this case, this representation will already easily reveal your cluster structure. So any kind of naive or relatively stupid clustering method will easily reveal the cluster memberships from applying that clustering algorithm to that reduced representation. Any questions?
아이디는 0인 벡터를 그러면 데이터가 원래 컴퓨터의 데이터끼리 3차원, 4차원의 표현 형태가 좀 가까이 있는 것끼리 조금 달라야지 좀 근데 이거 같은 경우는 같은 그룹에 있으면 아까 1, 1, 2, 2 이런 얘기를 생각을 하면 같은 그룹 안에 있으면 모두가 같은 데이터 표현 형태를
네.
안 좋은 그래서 클러스터링은 근거니까 상관이
그러니까 그 데이터 간의 서로 간의 그 difference는 무시가 되고 같은 그룹이면 하여튼 같은 벡터 표현형을 가지도록 아이겐 벡터 이렇게 만들어진다.
그다음에 그래서
여기요?
여기서 100이랑 1, 2, 2, 2 벡터가 같이 있고 저기 0이 나와요. 그러니까 질문이 트랜스포즈 L 곱하기 F 트랜스포즈 L가 0이 나와야 되거든요. 그래서 LF도 꼭 되는
그러니까 F, L, F 이렇게 되죠. 근데 이제 요게 0이 나오냐? 아, 오케이. 이것도 0이 나오고요. 이것도 0이 나와요. 그러니까 이게 다 1111이면 즉 이게 무슨 소리냐면 Okay, so the question is, let's see. So if we use this all ones as our vector that is multiplied on the left, and then it's like doing the row sum, right? We sum each rows, okay, and then the sum of the first row will be your first element, and the second element, and so on. And so in the case of F transpose LF, so we only consider this guy. This guy will become lambda times F, where lambda is already becoming 0. So at this point already, this guy doesn't have any effect. But what if we first compute this guy? Okay, so can we verify this guy by computing the multiplication with F and L first before multiplying L times F? Okay, so it's F transpose, and in this case the same analogy or same justification is also holding true. So in this case if we have all ones and then we have matrix L, and then the resulting vector will be the row vector. And then what is the first element? So the first element is the summation of the first column is this guy. Okay, and then our Laplacian matrix L is always a symmetric. So we are assuming the symmetric graph or undirected graph. So where is the example? So here in this example, so we always have the same values in the symmetric positions. So that way the row sum is the same as the corresponding column sum. Okay, so in this case because your matrix is symmetric, even though we compute F transpose L first, we will have the same result. So it is nothing but just the same eigenvalue, which is 0 times, it's all 0 matrix, right? And so we can still represent it as 0 times the same vector.
제 질문이 앞에 슬라이드에서 지금 1, 1, 2, 2가 저 WIJ 그리고 FI 마이너스 J 꼴로 봤을 때는 0을 만듭니다. 그래서 결국에는 저 1, 1, 2, 2를 F라고 주면 F 트랜스포즈 L, F를 0이 나온다 되는 건데 저 1, 2, 2가 그럼 아이겐 벡터라고 확신을 할 수 없고 LF 제 질문 F 트랜스포즈 F가 0이면 항상
그렇죠. 네. 왜 그러냐면 L times F 이게 0이면 이걸 물어보는 거예요.
거꾸로 F 트랜스포즈 F가 0일 때 LF
이게 0인지
네, 이게 전체가 0일 때 이게 무슨 뭘 뜻하는
네. 이게 그러니까 여기에 벡터가 이제 다른 게 들어가면 예를 들면 이제 x 트랜스포즈 l y 이러면 얘가 0이 아니어도 이 전체를 0으로 만들 수가 있어요. 예를 들면 이 벡터가 예를 들면 뭐 1, 2가 나왔고 요 x가 2-1이면 내적하면 0이 나오죠. 근데 여기서는 이게 같은 벡터가 들어가기 때문에 이게 이제 항상 요 가운데가 0이어야 이 전체가 0이고요. 그건 또 어떻게 이야기할 수가 있냐면 이제 L에 대한 이제 촐레스키 디컴포지션을 생각해보면 이게 이제 시메트릭 포지티브 데피니시라고 하면 이게 C 트랜스포즈로 이렇게 되고요. 그럼 여기다가 이제 F 트랜스포즈 L F 이거는 이제 F 트랜스포즈 C 그다음에 C 트랜스포즈 F 이렇게 되고 so C 트랜스포즈 F의 그냥 투놈이 돼요. 투놈 스퀘어드가 돼요. 그러니까 결국은 그러니까 정확하게 말하면 L 곱하기 Y가 혹은 L 곱하기 F가 0이 꼭 되어야 되느냐 그거라기보다는 요 부분이 0이 되어야 이 전체가 0이 되게 돼요. 그러니까 이거는 마치 이런 거예요. 그러니까 뭐 x제곱이 0이 x 곱하기 x가 0이면 이게 0이 아닐 수도 있는 거 아니냐 약간 네. 이게 0이 아니고서도 이거가 0이 만들어질 수 있는 거 아니냐 라는 이야기가 되는데 이거는 이제 알고 보면 결국은 똑같은 것과의 곱이기 때문에 이거는 0이 되려면 역시 하나가 0이 돼야 돼요. 이것도 역시 마찬가지예요. 그러니까 뭔가 곱해진 게 0이면 이게 0이 되어야 되느냐 이런 게 이제 굉장히 내추럴한 질문일 수 있는데 이게 L을 반쪽으로 나눠서 C와 C 트랜스포즈로 만들면 이렇게 되면 이렇게 똑같은 두 쪽으로 나눠질 수 있기 때문에 결국은 똑같은 두 쪽 중에 한쪽이 0이 되어야지. Unfortunately, from looking at your faces, I guess not many students understood this. Okay. Yeah. Yeah, probably. Yeah, with the Korean, I would have explained better. But at the same time, yeah, I think I did my best. And inevitably, understanding all these or kind of this, my explanation today will require some background in linear algebra. So I cannot probably cover all of them. Yeah, but you can take maybe your takeaway message is to study hard linear algebra. Yeah, you will see it very very often in your life. At least if you keep studying or if you conduct your research for years, and then I guess linear algebra is a quite versatile tool. So it will be it will be great to have a kind of a solid background in linear algebra, so that but at this point you can ask any questions even though you don't have any background. So please let me know. Any questions?
그럼 만약에 찾고자 하는 클러스터가 5개인데 나이 선배님이 3개, 너는 3개만
Yeah, that's a very good point. So yeah, is it really a practical way of doing clustering? So yeah, the student pointed the important part. So I mentioned that. So we have to extract out. So we have to pick out those eigenvectors corresponding to 0 eigenvalue. And then the question is, will your matrix L ever have 0 eigenvalue? So 0 eigenvalue, and this assumption is okay. So you always So you always have at least one eigenvector corresponding to 0 eigenvalue, which is, I mean, regardless of any graph, this eigenvector of all ones, that will trivially make your F transpose L times F to be 0, right? But if you have a two clearly separated blocks, and then you will have two eigenvectors, linearly independent eigenvectors corresponding to 0 eigenvalues. But will your graph be clearly separated? Is it always the case? So, what if your graph is having a high edge weights within each group, but you may have some edge weights like 0.01, 0.05, and 100, 500, and 10, and so on. So in these cases, these edges are not zeros, and so we have 3 and 4, 1, 2, 3, 4, 5, 6, 7. In this case, we will see some non-zero edges here, but hopefully they will be small. So in this case, you will end up with just a single eigenvector corresponding to 0 eigenvalue. So in this case, in practice, the graph of the eigenvalue let's see if I have okay, so this is some example or some experiments using some synthetic data. So this is just one-dimensional data. So your data or your feature vector is just trivially one-dimensional, and then this is a histogram over your one-dimensional space, and then you generated like this kind of data from 4 Gaussian mixtures, and so each Gaussian has a really small variance, and then they will have really clear separation. And then how do we perform, or how do you apply this graph Laplacian and Rayleigh quotient and things, this kind of spectral clustering on this kind of feature vector representation? So we originally have a feature vector representation, and so suppose we have 100 point here, and then we will form 100 by 100 adjacency graph, and then how do we compute the how do you obtain the edge weights? We do some Gaussian transformation, right? So if we have some edges, if we have some distances, and then we do this kind of thing, minus sigma squared, and then d squared, right? And this guy is already giving you some, this guy will have like a fully connected graph. So there will be no zero edges. All the edge weights will become non-zero, right? So in this case, it's already not holding true in terms of this subgroup or sub-block structure of your matrix. So you no longer see like this kind of subgraph in your graph, right? So in this case, your pattern of eigenvalue after performing the eigen decomposition on the Laplacian matrix, they will have this kind of pattern. So this is still assorted values of eigenvalues, okay? So you clearly see at least 1 0 eigenvalue, because all ones will trivially make F transpose LF 0, right? But after the second one, it will have already non-zero eigenvalues. And then it will have this kind of pattern. And here in practice, what we do is, suppose you want to, so still the number of cluster is your parameter. So it's suppose that is 5. And then what you do is you pick up 5 eigenvectors corresponding to the 5 smallest eigenvalues. Okay. So that's how you apply this kind of spectral clustering onto this noisy graph. Okay. So in this noisy graph, in summary, you pick up the predefined number of eigenvectors, where this predefined number is the same as number of clustering that you want. Then those eigenvectors will form your new feature vector representation by looking at each row corresponding to each data item, and then do some simple clustering like a k-means. Okay, so that's the overall procedure. 답이 됐어요? 질문. Okay, although time has already passed a lot, but let me just quickly finish this chapter. Okay, and then although if you recall what we learned last time, and then we have a kind of sudden jumps, logical leap, which is not closely connected, and that is this. So we discussed about this normalized cut, like a mean cut and normalized cut and so on, right? And then theoretically, if you construct L and then this kind of normalization that we briefly discussed, okay? And after normalizing your Laplacian by this way, and then performing the eigen decomposition, and then doing the k-means on the eigenvectors, and then theoretically it is known that that clustering is trying to minimize this normalized cut. But fortunately I'm gonna skip that part. So that's the connection between this normalized cut and this Rayleigh quotient from Laplacian graph or Laplacian matrix. Okay, so let me briefly go through this algorithm. Then we obtain first this normalized Laplacian matrix. Okay, so we first compute the edge values, edge weights as some similarity measure from maybe feature vectors, and then this graph will be positive semi-definite, and then and so on, and then perform the eigen decomposition, and then pick up the k smallest eigenvectors, and then using rows as a reduced dimensional representation, we perform some simple clustering such as k-means. So that is it. And then these are some results. Okay, and then it's in some sense it's quite surprising that this these data as one this clustering algorithm or spectral clustering algorithm identified this kind of weird shape of data as one single cluster. And how did this spectral clustering reveal this kind of cluster, this arbitrary shape? It is not mainly like exclusive advantage of spectral clustering, but it's advantage generally in the graph-based clustering, similarity-based clustering. Okay, so in this case, if you imagine the pairwise graph matrix or our adjacency matrix, although we will convert it to Laplacian matrix, but this similarity matrix will have the close relationship between these two data items because they have really high edge weights or really small distances. So that way, even though this guy has very low edge weights to this guy, in terms of a graph, as a whole, this group will have a tight relationships compared to other groups. Okay. So these are some other interesting results. But depending on the number of clusters, which is a predefined parameter that you have to choose in advance, yeah, it sometimes will merge some clusters. And then this paper was submitted to this NIPS 2001, although it's almost like 17 years ago. But yeah, it showed this nice little cute result from their clustering algorithm. Okay, that's it. So let's take a maybe 10-minute break